First, Alexander Marins will be giving talk. So, please, Marins, you can start.
Okay, I will try to share my other computer here. Let me know if you can see my screen. I will try to share it. Just a second. Okay. Well, nice. Can I start?
Yeah, we can see it.
Perfect. So thanks so much for everyone in this conference, and also thank you for Professor Sami, who asked me to come and give some updates about our work. Today I will give some brief and wide instruction about our work considering the Bingo Radio Telescope, mainly the current stages, our goals, and the next and futures goals we have. Okay. So the outline here is basically what is the main goals from Bingo, which data we are trying to provide for community, and also how it is working, and give some preliminary ideas how this type of radio telescope exploring radio frequencies can operate and provide data, and also give some ideas considering cosmology and constraint on cosmological parameters. And in the end, we discuss the next step for our goals, mainly for the second phase of being telescope, considering low scales. So we can, for instance, split our goals, mainly considering physics and astrophysics in cosmological way, in these six topics here. First of all, our main goal is, unfortunately, they are right here, but the main goal here for us is to observe neutral hydrogen from the universe, and using neutral hydrogen, we would like that try to detect baron crystallizations. That is a way to provide a lot of types of constraints in cosmological parameter, and also to provide a standard way to calibrate distance. For the second step of the bingo, the goal will be to observe compact astrophysics sources like FSR radio bursts, FRB, quasars, and pulsars. Well, we can explore, since we can use neutral hydrogen as matter tracer, we can try to, we can not only try, but we can use it to study different physics mechanisms and cosmological models. For instance, we can try to constrain neutral masses, neutrino masses, explore primary no Gaussianities, or even no Gaussianities from our data, as I will show and follow, and also constrain the geometry and dark energy dark matter models. So, okay, since we want to have a radio telescope exploring radio frequencies from the universe, the idea is because from neutral hydrogen we can trace the radio modular distribution. Since after, for instance, cosmic microwave background, because from this part of the universe it's possible to have an coupling a formation of neutral hydrogen, what wasn't before this time, and it's not all the whole history of the universe after the CMB possible to observe neutral hydrogen, but for our goals here, that is after reionization, we can use even weaker, but we can use neutral hydrogen to observe, to trace the modular distribution mainly from 21 centimeters signals. And how we do it? In the first moment, using a single dish radio telescope, as I will show in this next slides. The goal is simply we map in the sky with a broad resolution, not so great, but collecting all information from certain region of the sky and scanning the sky using the rotation, the Earth rotation. So in this way, we are not target to observe its source like what happened, for instance, for gas, but we are collecting the hue in integration, the hue intensity for some region of the sky, some pixels. And in this way, we can, for instance, have an intensity description for this region of the sky that we will scan, and also provide a three-dimensional image from the sky, since we can observe it in a certain frequency range. And we can translate, for instance, since we have 20 centimeter emitted from source for this specific wavelength and specific frequencies, since the universe is expanding, we can know the redshift that this data come from. And in this way, we can have a three-dimensional observations. Okay, of course, the Bingo is not the only one telescope I mean to have this type of data. Here I'm showing only some of them. For example, even in India we have Sarat, we have GMRT, but here I'm showing the other ones, for example, interferometer wave time. That is known because of mainly FRBs. It's a good FRB hunter. We have also in Netherlands and French LOFAR, and in India, in China, where I'm living in now, we have in Xinjiang province in Tanai, and also from Guizhou province FAST. We have, of course, SKA in Australia and also Meerkat from Australia and Africa. IREX also from Africa, and we will have, for instance, Bingo from the Soviet Hemisphere, but concentrated in Brazil. The idea is because we don't have much telescope in the software hemisphere, celestial hemisphere, and mainly, for instance, this type of design that is called the single dish. So the Bingo will be in a very quiet region that is not much affected from radio frequency interferometry, and also a good way to observe the full sky, not the full sky, but the sky that the project is having to observe it. The artistic design is like here in where we have in this right side here. This is the final design that it has been built in. For instance, in this moment, Bingo is like in the top, in the bottom pictures. We have the side, we have prepared the location when we have our dish, that each dish is basically 40 meters in diameter. And we, for instance, part of this dish has been shipped from China, and the feed horns that we collect the signal from the sky and transmit to the digitalizers have been built in Brazil, for instance. So in this moment, we have basically everything prepared to compute in this telescope in Brazil, with part is inside in this moment, but part has been shipped from China. Here we have a picture showing, for instance, part of our PIs, Professor Abdallah, Professor Milk, and Professor Felipe Abdallah, in a collaboration with a company from China. The same company that has been built for SK has been built for Bingo 2, the place, and they have visited this place in the middle of this year. For the next slide here, I will present, for instance, a brief description how is the Bingo design and the main configuration of the Bingo. For instance, Bingo is a single dish when one dish receives the main source from the sky, the light from the sky, and this is then focalized in a second dish, and then in the feed horn is collecting in the focal plane collecting the signals. The idea is basically to minimize cross-polarization and have a low polarization leakage, mainly because 21 centimeter is not polarized, so we would like to have more intensity stope parameters and a very low level of other stope parameters. So the design has one of the most important goals to conserve the intensity stope parameters. Currently, as we show in some preliminary works, the design is considering 20H feed horns in this focal plane here, where each feed horn can have a vertical movement to cover a homogeneous region of the sky. Okay, but actually, which region of the sky being we will cover? Okay, I will not get into the very experimental informations because I believe it is not the goal here, but I can answer later if it is required. But the idea here is basically is to cover this region of the sky when they are rock as converged. It has a region when we can remove certain parts of the galaxy that is very important contaminating for our signal. And for instance, here we are covering 30% of the sky for redshift is between 0.13 and 0.45. And to have a notion how weaker is a 21 centimeter signal, that signal from the neutral hydrogen, considering galaxy, for instance. I have a total here in this plot as 41 total. That basically has synchrotron emission from our galaxy, the Milky Way. And we have here more than 10 over 3 millikelvins higher than 21 centimeter signals. So this is a challenge for us to be accurate to remove the contaminants because Bingo cannot distinguish which signal, even Bingo, not only Bingo, but all intensive magnetic radio telescope cannot distinguish which type of source is emitting, but only collecting this radiation inside a certain frequency range. So since we have a very weak signal, it's a challenge to estimate the signal from the original data collected. Okay, so just to have a notion how this is processed, for instance, in the next slide here, I'm only giving a simple way to show the whole idea. When a source from the sky in this covered region emits a radiation, these radiations so touch the main dish when then reflected at other dish, and in the end it is focalized on focal plane specifically for feed horns. And on the bottom we can have, for instance, a design here for the focal plane. And considering, for instance, only one feed horn, we can process this data as an equation here, basically the instrumental noise, the observed data in V, and the data from the sky in T, but also some information from how this radio telescope can observe it in resolution, also how is the scanning strategy to cover the sky, and the gain from the radiometers and so on. For instance, in bottom right panel, I'm showing only one example, for instance, for TOD, consider this feed horn here for 1 day. When we have a very high signal here, because I believe this is here for some. Okay, so here, for instance, we can see the whole idea as well. When the bingo will cover this region, here is a simulation that we show in this work here for Bingo Project 3, the paper that we submitted and we published in this year, 2022, showing, for instance, a snapshot the region covered for each feed, each bin, but also we can move these bins because we can move vertically our feed horns to cover and have, for instance, a very homogeneous description of the sky. This is the most interesting characteristic of this design. Consider, for instance, the first design proposal for Richard Bach and other colleagues we have, because this design can have a very homogeneous description, and then is for processing this data is very useful. Okay, and also, for instance, we can see from these physical parameters that this type of simulations and following all characteristics from Mingo, we have a very good low polarization level and conserve the real data from the neutral hydrogen. Okay, but Bingo itself has a lot of steps and stages that each one will work and help us with some data and informations. Stage 0 is more instrumental when people will calibrate have been calibrating our instrumentations, receiver, feed horns, and so on. Stage 2 is more post and pre-processing data, registering time order data, providing some maps, recorded transient objects. Stage 3 and 2 and 3 is for simulations, and providing techniques to estimate 20 centimeters, as we will see in the next slides. And for instance, stage 4, when we are investigating different models of cosmology building, as this mentioned here, dark energy, modified gravity, FRBs, neutrino, and no gravitations. Okay, I will not describe in details how we can estimate neutral hydrogen itself, but I will concentrate here in this bottom left, bottom right images, when we can see, for instance, when we observe or simulate a sky, we are not directly seeing 20 centimeters. So we have in H1, a simulated H1, we have a simulated instrumental noise, where here I'm only concentrating in white noise, and we have a simulated foreground from mainly from our galaxy. When we try to model our foreground in this data, and remove this model, we cannot only remove this model, but we also introduce some leakage from foreground. So even if you have a good accuracy to reconstruct foreground, as in this bottom plots here and the left, even though since our H1 signal is very weak, the difference between them is not exactly H1 plus voice. How we can see it basically is because even if you remove from this estimated foreground emissions, we remove this instrumental noise, we will see the H1 patterns, but we will not see exactly the same simulated H1. This is because we have a leakage from this data of H1, and also we have leakage into this data because of foreground. So we needed to bias this data and then obtain some estimation for our data. And here, for instance, in the next step, we have statistical information from a two-point function in the harmonic space, angular power spectrum, where we can see, for instance, in red colors, we have simulated data. In green color, we have the instrumental level that is lower for low L's, but higher for high L's. Higher dependent on the instrumentation we are using. And in bullet blue data here, we have this estimation that we can provide this things we have contamination in our data. And after we devise this information because of the leakage and also because of the white noise instrumentation. And as we have shown in our work, we can have and achieve a good accuracy for this data even if you have a very rich signal. That is very wonderful for us because can prove that we can use this type of data to provide constraints and independent data to constrain cosmological models and cosmological parameters. Okay, for instance, think about science in terms of observables and cosmology. We can, for instance, see how we can obtain and preserve Bow baronical acceleration from bingo. And in this work, Camille and Weiss proved that since we can simulate 21 centimeters and use a certain template, we can, for instance, and also the cosmology will depend on how we are measuring these scales. We can have this parameter alpha, that alpha will provide if you are in an accuracy with the fiducial ratio between angular distance and RD. For instance, if you try to use MCMC to do it, it is expected, for instance, for our simulation will depend 1 to provide the fiducial as the best fit. And we actually can recover in a good accuracy with the simulation, and after remove the fragment, we can actually measure parametric oscillations. Okay, we can also try to measure the neutrino masses, and currently one of our collaborators has tried to constrain the sum of the Damascene neutrinos and use it as in cosmological information. I mean, consider how this can affect, for instance, thermal velocity and the power spectrum amplitude. Okay, but we can also try to constrain dark energy and dark matter models, for instance. Currently, we could present and publish 2 works, mainly 2 works. One for in this paper here, as Vidal et al. It's called the Bingo Project 1, and also one paper because of published for by Andre Alencar, the Bingo paper 7, when we are trying to, for instance, here constrain H1 bias and omega bias. They are very important parameters for neutral hydrogen cosmology, but also this published has constrained double CDM cosmology in a feature makes analysis showing, for instance, bingo in synergy with other telescope, other observables like blank that constrain the other informations with the bingo constrain the later informations. We have a good accuracy to constrain in the future this type of model. And here in the left panel, we have a work that has been will be submitted soon. It's basically finished showing Monte Carlo constraints for the lambda CDM and showing a more accurate and complete analysis for bingo in different situations and mainly in synergy with bank. And showing basically that when bingo is in synergy with the plank, we can have and achieve a good accuracy. Not only double CDM and lambda CPN, but we also can try and provide a good data to constrain other type of models like CPL, dark matter and dark energy interaction models. If someone is interested to understand better how it's done, I really recommend scan this code here and assess these works that will be describing details of these equations and which model is assumed. Okay, I believe I have 5 minutes or something like that. Well, so I will just skip some information here, but we can use, for instance, notation for all both for remote information and also for systematic information. But here I will show other paper we have published soon. It's not in archive, but it has been submitted to Astrophysics Journal. We are showing the synergy between H1 and wiki lensing, CMB, and also galaxy lensing. Firstly, we show the challenge we have when we have this cross-correlation, mainly because the most part of this data is basically leakage. We don't have this data because of the degeneracy we have with H1 and foreground for long wavelengths. But also we can show exactly in a very simple way, explain the origin of this information leakage, and also the potential of this information when we can recover the amplitude of this data. What is very interesting, because we are not using this type of cross correlation so far to provide a new independent information, even for H1 or for cosmological constraints. And we are providing another paper to be submitted soon as well, showing the constraints that this type of data can provide for the community. And the last minutes I have, I would like to say a bit more about the next step for Bingo, because I have shown for us what Bingo is, what Bingo wants, what Bingo has done, even we are not operating it. But we are thinking also for the next years, not only cover large scale of the sky, but also to observe the small scale of the sky. In this way, we are working in ferrometric analysis in two ways. One is providing that feed horns as triggers, where we spread over our site in Brazil, and also using phase arrays. It will be nice. We have, for instance, so far 2 papers showing this particular new goal of the Bingo, mainly to observe fast radovers, and we are showing the potential of the Bingo to observe this data. That, for instance, time is a very nice, have done a very nice work to observe fast radovers. And also, not only this, using, for instance, phase arrays will provide Bingo to cover a very large region of the sky. Basically, we will be able to cover half the sky, and also to cover a higher region in redshift. For instance, achieving a redshift basically up to 2 or 2.3, basically. And for instance, when we say about phase arrays, that is a new technology that we can, for instance, observe with this type of technology for SK. But here we have a bit different method to do it in collaboration with our colleagues in Netherlands. When they are using default antennas, that is this one here. We have these antennas, and in this picture I'm showing 40-volt antennas, and 40-volt antennas you compose a tile, and each tile is a block of an station. And the idea is that my station will or 1-2 stations can provide interferometry, and also we can provide a third station and then have a better accuracy to detect not only observe and localize, but detect actually efforts. And for instance, we can show in a paper that has been submitted, will be submitted soon, that this type of observation is also nice because it can cover even the current Bingo dish, provide a good accuracy for observation with intensity mapping observations. if someone here doesn't know, for instance, what actually FRBs means, basically FRB is a very interesting astrophysical object observing radio frequencies, and one of these characters is to be a very time scale, basically time seconds, and no one so far know exactly what the physical origin of this phenomenon. They are very bright and very fast phenomena, and we can observe, for instance, from radio data. This data here is from FAST, published this year, and this data here is from HART. So we can observe this data here and use this type of information from this so far not known phenomenon to provide constraints also for cosmology. And in recent work we have published, we use the simulation we are doing and using the next step of the bingo to constrain, for instance, lambda CDM, astrophysical parameters, and also the different dark energy, dark matter models. So if someone is interested, I really appreciate in introduction of this paper here when we are showing the potential to use this type of data found in the bingo configuration for 5 years and 3 stations, two and 3 stations to constrain models from the cosmology and dark energy, dark matter models. Well, to wrap up here my presentation, some final remarks I would like to say is basically, well, the big telescope has the main goal to map the scan and map the neutral hydrogen from the South America, from south of our Earth, to observe the southern celestial hemisphere, and also to be one of the main telescopes to observe and register baryon constellations, which will provide us an ability to use this information to study better our dark star cosmology, for instance, dark energy and dark matter, also beyond general relativities, and for the second bingo stage, also use compact astrophysical sources to provide more information about our universe. In terms of the current stations, bingo is hoping we have our full operation by the middle of 2025, the next year, since the most part of the bingo has been done. And of course, we also needed to provide some calibrations in advance, but we are hoping to have this operated by the middle of 2025. Well, and we can also have a good synergy with other telescopes and other observations. Just to highlight, for instance, on a good synergy with FAST and China that are two very important telescopes here in China. That's my presentation for today, and I'm very happy to respond and answer any questions.
Yeah, thanks, Professor Marin. Let us see a few questions. Any question?
Could I ask a question?
Sure, please.
This is Roy Martins. Thanks for a very good talk, Alessandro. I just wanted to ask you, is there any possible synergy between bingo and meerkat in South Africa?
Well, possible. I believe it's possible. I don't remember in the top of my head, which region of the sky that meerkat has been operating. Since we have overlap between the regions, it's possible.
Yeah, it's a wide field survey with intensity mapping for cosmology is being proposed. And the idea is about 4,000 square degrees. It hasn't yet been approved, and it might only start next year with 1,000 square degrees. Probably going to be overlapping with various southern galaxy surveys. So there will definitely be some overlap with Bingo, but I'm not sure how much.
Yeah, the way investigate, well, I believe I talked with Mario recently, but I don't remember if you talked about it. We will investigate it. Well, it's a good synergy if it will be possible.
Yeah, I think it makes a lot of sense. Thanks again for that talk.
I have one question.
For sure.
Yeah, so this is regarding you want to study FRBs as well as you want to look at dark energy. So FRBs are transient events, and then how are you going to, as a problem with respect to timing of the observations? So you will just observe and then looking at for dark energy, and then if the FRB comes, you will just worry about it. How are you going to do this as a logistic?
Okay. I couldn't say because I was trying to only give an overview, but here, for instance, yes. Because the intrinsic flux from the FRBs is related with the distance. And as we know, for instance, when we measure distance in cosmology, we can also study our universe and constraint parameters. So this is the straightforward way to think about how we can study the dark energy and using FRBs because of this relation between intrinsic flux and the distances.
Professor Marin, I have one question regarding neutrino mass. Regarding neutrino mass, so we have 3 active neutrinos. You are mainly concerned with those probably, but suppose if there are sterile neutrinos which has certain amount of mixing with these 3 light neutrinos, can that mass also could be taken into account in your experiments or no?
Well, to be honest, I have not doing this work here. Is a Lim Fan Xiao, is a collaborator is a Chinese collaborator work in South Korea, and so specifically, I'm sorry, but I will not be able to answer if it is possible or not. Okay. This is only a theoretical investigation.
Okay. So
because in this work, for instance, he is showing how this can affect the observed Pauli spectrum, and if it is possible or not to observe the effect of this three neutrons. But this distinguish I cannot. I don't think so.
Okay, if there are no more questions, let us thank again Professor Marins. Okay, thank you. So our next speaker, Professor Kinjal Luchan, he will be talking about quantum effects in late-time cosmology. Okay.
Hello. Am I audible? Okay. So I must begin by thanking Professor Sani and Bhagavatam for inviting me here. What is rather magnificent set of collections of people who are talking very interesting things about cosmology, gravity, and astrophysics. And it's my pity I could not attend it for full duration because of my engagement at my home institution. So today I'm going to talk about late-time effects of quantum cosmology, and particularly focusing on quantum effects in late-time cosmology. This work I have done in this work was initiated in collaboration with Pradeep, Professor Padmanabhan, and rather afterwards, after his demise as well, we have been carrying on this work. So it's partly a tribute to his vision about quantum cosmology as well. Okay. So I start with this standard picture which many of you might have seen already. So this depicts our collective knowledge of how the universe has evolved, which begin probably at a very early phase in a quantum gravity framework, which should replace something called classical Big Bang singularity. Afterwards, there was a brief era of accelerated expansion, which we typically understand as inflationary epoch. And then afterwards, when the inflation ends, the classical cosmology took over, and we had the gradual successions of radiation-dominated phase, matter-dominated phase, and presently, we are supposed to be in the dark energy-dominated phase. One parallel line of thought which is running across this theme of evolution is that we were born quantum, the universe was born quantum, as a very nascent and very tiny object, and then there was some quantum gravity-dominated phase which we do not have clear understanding about. And then there is some hint of accelerated expansion of inflation where quantum gravity probably was off, but still quantum matter was working in a quantum fashion. Matter was not fully classicalized. Our understanding of the observations from the data and other things also suggest in such a way, some way that at the end of the inflations, what inflation supplied us was initial conditions for classical evolutions. So afterwards, Einstein's field equations can be used to describe the universe, and we can drag these equations classically to see whatever effects inflation handed us over, how do they reflect to us at the end of the, let us say, matter-dominated era when dark energy took over, and how of those imprints are imported in CMBs, most modern observations, which we see today. So this is the depiction of the Planck's data, which is looking at the CMB's anisotropy. So this red dot and blue dot you might have seen so many times. They are trying to tell you about departure from the background value, and this looks like a case for a perfect black body, more or less 10 to the power minus 5 is the scale of deviations. And the idea is looking at this, how do we know, how much do we know about the primordial seed of the universe which was implanted in the evolution history through inflation. Okay, so that the standard analysis which is adopted is that whatever primordial seed inflation implanted into the evolution, if I take it further for large wavelengths, when they cross the local horizon at the, let us say, matter-dominated era at large scattering surface, they get down by 1/10th of their initial value, which is the primordial seed, and they get frozen afterwards if they are evolving in matter-dominated era. So looking at the modes post-horizon crossing, and once they have crossed matter-dominated era, basically we are looking at 90% the 90% value of the initial primordial data, and that reflects in the CMB temperature anisotropy. So CMB anisotropy through this channels of thought is connected to the primordial seed inflation was having. Now the question is, looking at it, can we say that the universe was necessarily born quantum, and at any stage did it turn classical, or if there are signatures of its quantumness still persistent in the CMB data what we have? Okay, this story has a very long origin, and actually Padmanabhan was one of the first people to start discussions among that. This is a paper from 1989. This is the idea Paddy was proposing at that time, that we could look at the classicalizations of gravitational or matter degrees of freedom as an act of decoherence by tracing out uninteresting degrees of freedom which we do not observe readily. At that time, Halliwell was also looking at those data while tracing out the outside horizon modes to turn things what is available in visible universe classical. So this is a process of decoherence by tracing out unnecessary degrees of freedom which we do not have access to or which we are not interested about, to turn the visible sector into something like a decohered classical kind of state. However, there is a debate about whether things which have decohered are completely classical or they are statistically classical. Okay. So this is the same discussion in most modern avatar, if I could say, that where people try to obtain the description of the universe in more something like some statement which is famous by the name of decoherence without decoherence, that they do not want to trace over things which are uninteresting, but want to squeeze initial data into a particular fashion in the phase space, such that the average description, statistical description, mimics something from a classical ensemble. Okay? So the typical game in this neighborhood is obtained by solving for the mode functions of a field. Let us say we are discussing about a field, with scalar field, let us say, and we want to see its evolution. In FRW universe, which is in which the fields are evolving, their equations of motions are controlled by the generalized Klein-Gordon equation in curved space-time, and this equation ultimately evolves from their conjugate pair at time t is equal to 0. Let us say yk and pk are the conjugate pairs in the phase space. At later time, they will evolve to this yk eta and pk eta from over time evolution. Now, one can see that if the evolution is of such a kind that one of the pair F1 and G2 or G1 and F2, one of these pair grows very large, then it would so happen that Y and T will get linearly correlated. That means whatever you could, the one conjugate variable you can talk about could be known from its canonically conjugate operator, which is somewhat unlike quantum mechanics where you have to have information of x and t separately from information of x p could not be obtained. But in this description, where you squeeze your distribution in the phase space along a particular direction, this is possible. This correlation can get built up. And this is what the most modern predictions are about. That the inflation, what it did was to squeeze the initial vacuum state into a highly squeezed distribution in the Wigner space or phase space, something like this. And therefore, whatever observations which we are able to do on this data is equal for this quadratic system, which is a free field theory, is almost equal to a classical ensemble average. So this is a mathematical machinery from which you can say use of classical theories is good enough to compute expectation values. You do not need to go quantum for that. However, again there is a question, is the expectation value the only criteria to describe universe being classical or quantum? So here there are many set of thoughts where people try to look at not only expectation values but correlators. So remember, most of the quantum properties of any system is hiding in the correlators or interference terms. So therefore, in the squeezed kind of state, the inflation, what it does, it takes the initial vacuum state and gets you a squeezed state